Okay, so to recap from last time, we were talking about what happens when I kind of change the sampling rate of a signal, right? So last time, we kind of talked about two new blocks, right? One was kind of what I would call like the downsampler or the compressor. And just remembering what that means, that's like saying if I have some signal, it's like saying I take every, mth sample. And then we had kind of a similar operation called an expander. And so what that operation does is it takes a set of entries and it puts, an extra bunch of zeros in between every entry. And then we talked about how if you ran this through a low-pass filter, you could recover kind of like an interpolation of the signal that would, be the correct set of samples in between the elements that were here, right? Assuming that I sampled with the Nyquist rate, I could reconstruct those middle samples, right? And just to refresh our memory, what's happening in the frequency domain, right? So when I downsample a signal, I could have problems, right? Because suddenly I could go from a signal that has been sampled properly to one that is not sampled fast enough, right? So I have the danger of introducing aliasing by downsampling. Upsampling, nothing can go wrong, right? Because if I sampled above the Nyquist rate already, then I can't possibly screw anything up by adding more zeros in the middle, right? It just means that I am kind of squishing the frequency domain. So let's just do a quick recollection. So basically, if I do, downsample by m in the frequency domain, so if this is my original signal, maybe I should scratch this out. So if this is my original signal in discrete time, again, this is a DTFT, so it has to be 2 pi periodic, and let's suppose this has height 1, and this has some band limit omega b, right? So if I downsample by m, what happens is that each of these copies spreads out by a factor of m and also squishes down by a factor of m. So kind of what I get is something like this. Right, so each of these guys is 1 over m as high as it was before. And this band limit now becomes omega b times m. Right, so unless omega b is pretty small, or m is pretty small, then it's likely that as I downsample, things spread out and I could possibly get aliasing in here, right? On the other hand, if I upsample by a factor, what happens is kind of the reverse, right? Instead of things spreading out and squishing, I have things that basically go like this. So I have something that looks like this. Again, I have 2 pi periodic copies. And these guys now occur at omega b over L. And these copies occur at 2 pi over L. So it's kind of like saying that I take my whole DTFT and I squish it together. Okay. And in this view, you can kind of see why a simple low-pass filter that occurs every, that's 2 pi periodic, can just notch out the copies that I need, resulting in what I would have gotten had I sampled the signal at that higher rate. Okay. So, things can go wrong when I downsample. Things really can't get screwed up when I upsample. Okay. Okay. And so, one thing that we talked about here was that I could mitigate the potential problems of downsampling if I first were to low-pass filter the signal to prevent this possible spread, right? So if I were to low-pass filter the signal, what would I need to have a band limit as, right? My band limit would need to look like, so let me just say, prefiltering to prevent aliasing when downsampling. What I would do would be to first pass this through a low-pass filter where the low-pass filter had a band edge that looks like pi over m. Right? That will basically, make sure that on the one hand, I will lose some high frequencies inevitably, right? So I'm losing information. But on the other hand, I'm not kind of corrupting the information that I do have when I do the downsampling. And so it's kind of like saying, by doing this, I am automatically making sure that my downsampled input, that my input to the downsampler doesn't violate the m times the Nyquist rate, right? I'm kind of making sure that nothing bad can happen. And then I would pass this through the downsampler to get my, new signal. And by the same token, I have a low-pass filter to interpolate missing values when upsampling. Right? So if I wanted to upsample, what I would do would be to take my expanded signal, the one with the zeros in the middle, and then I would pass it through a low-pass filter. And that filter looks like this, where I have basically pi over L here, and there needs to be a gain on this filter to make sure that the copies have the right height after I do the process. Right, so we kind of talked about both of these things last time. So these blocks with the up and down arrows are kind of simple mechanical blocks that simply take certain samples and put zeros in other places, right? These low-pass filters act to kind of do the right thing in the frequency domain. Okay. So let's stop and ask if there are any questions about this kind of review, right? This is kind of where we stopped last time. Okay. So last time we were making the kind of explicit assumption that L and M were integers, right? That's like saying I downsample by 2 or I upsample by 3, right? So the most I can do in that case is kind of these very limited changes in rate, right? But it's certainly common in some real-world systems that there are, some systems that just operate. They expect their input is going to be given at a certain rate, and that rate is kind of pre-specified. And so what I may need to do is I may need to bring my input signal down to that rate or up to that rate for the next block of the system to actually work, right? And so I am often in the situation of having to kind of modify my sampling rate by kind of an arbitrary amount, right? I may need to go from a signal that sampled at 10,000 hertz to one that sampled at 12,000 hertz, right? And so in that case, I need to, think of a way to do this that is relatively computationally efficient, right? So one thing that I could imagine doing is, okay, so what about changing the sampling rate by a non-integer factor, tau, okay? So what I could do is I could say, okay, I'm going to approximate my tau as some rational number, say m over L. Okay. And then I could basically try to make a combination of an upsampler and a downsampler that would achieve the right rate change, right? So what I could do is I could say, okay, here is my original signal that has period t, right? Now I put this through a upsampler, And again, I've had something that looks like this. So again, this is the same picture I drew on the previous slide, right? So this whole thing is going to be like my interpolator. So now, at this point, I have this kind of interpolated signal, and the rate of this signal is T over L. Right, that's the sampling period, right? This is like saying that, if before I had samples every, say if I have T equals 20 and L equals, 4, that means that now I have, instead of having samples every 20 units, I have samples every 5 units, right? That's like saying I'm sampling faster. And now I would put this through something that is going to, again, spread the samples out again. So what I would do is have my kind of block here, where to be safe, I would first do the prefiltering. So this is my kind of preventative filter to avoid the possible aliasing. Then I'm going to downsample that, and then my output signal, which I'm going to call x tau of n, basically has now a rate T times L, T over L times M, right? And this is approximately equal to tau, right? So say, for example, that M equals 6, then at this point, this is going to be like saying I'm sampling the signal every 30 time units, right? So what I'm doing kind of here is I'm saying, this would be kind of a dumb example, actually. Maybe I should do like M equals 5. So here, my T would be equal to 25. So that's like saying that my old sampling rate of the continuous time signal was every 20 units. My new sampling rate is going to be every 25 units, so I'm going to have like slightly different samples. And I've accomplished that by basically doing a bunch of discrete time operations. Okay, so assuming that the signal was originally sampled fast enough, if I go through this kind of cascade process, I can ultimately kind of resample the signal at whatever rate I want. And I can make a little bit of a, I can make a little bit of a abbreviation here, because here it's like I'm passing the signal through 2 low-pass filters sequentially, right? So only one of these low-pass filters is kind of going to be binding, right? Depends on whether L is bigger or M is bigger. So what I could do is I could say, I'm going to take my original signal, I'm going to pass it through the expander, then I'm going to pass it through a low-pass filter that has height L, and then this bandwidth is basically the minimum of pi over M or pi over L, right? And then I put this through here. Right? So in this way, only one low-pass filter is required in the middle. Okay. And so, just to kind of be clear, so if M is greater than L, so remember my tau I was approximating by M over L. So if M is greater than L, that means that I have a net reduction in sampling rate. And what that means is that the more binding of these two numbers is going to be the pi over M. So that means we need the pre-filter to possibly prevent aliasing. If M is less than L, I have a net increase in sampling rate. And that kind of means that this number is more stringent, and that means I don't need the pre-filter, so basically no pre-filter needed. No aliasing can occur. Right, so I really only need one filter either way. Okay, so let's stop to ask, does that make sense? questions or comments? So this is just kind of a combination of what we learned so far, right? And so now if I need to change the rate by, for example, like 1.2, which is 6/5, that would mean that I have something where I upsample over here by 5 and I downsample over there by 6, right? So that means that there's a way to accomplish things that are kind of nice, you know, kind of close to rational factors. And if I had something that was like, you know, 1.287, right, then in theory I could have something that would be, you know, upsampler by 1,000 and a downsampler by 1287, right? Now you start to see that this doesn't really make a lot of sense as you push the numbers L and M to be very large, right? So for example, you know, even if my tau is really close to 1, so say for example, I have tau equals 1.01, right? That would be like saying, okay, I would choose my M is equal to 101 and my L would be equal to 100. And so this would be bad, you know. So I'd be basically having big intermediate changes in rate. To get back a signal close to the original rate. Right? So why would I want to, you know, suddenly, you know, balloon up the signal with 100 times the extra number of samples and then throw almost all of them away just to get back down to something that was about the same rate, right? So the question is, can I do this kind of process more efficiently, right? Do I have to introduce all these zeros and do this filter and then throw away almost everything that I had, right? And the answer, of course, is yes, there is a smart way to do it, okay? And so the answer is what's called multi-rate signal processing. And so I'm going to just kind of touch on this today. This is definitely something that has a much wider application. So again, this could be an interesting project idea, is exploring multi-rate stuff a little bit further than what I'm going to talk about today. So, multi-rate signal processing. Lets us avoid kind of unnecessary computations. Okay. So to talk about this kind of stuff, I need to introduce a couple of little intermediate theorems, or what I call lemmas, okay? So, you know, useful, I guess, what I would call identities. So one is that if I have a system that looks like this, where first I downsample a signal, I get some values, and then I put that through some transfer function, and I get back some, you know, YA of n. It turns out that I can interchange this order in a certain way. And so let me write down what I mean. So basically, these turn out to be the same system. Okay. So let's prove what this means and why it's true. So the first line is something that we kind of already should understand, right? So we know what it means to, you know, remove all these middle parts of the signal, and we know what it means to filter the signal, right? So what is this guy here? So this is just another, you know, digital filter, right? So let's just make a quick note. So what is h of z to the m power? So remember that, you know, h of z is equal to the z transform of the original signal, right? And so h of z to the m is just what I get by plugging in z to the m into this formula. I guess these should be H's. And so this is actually, if I think about it, what does this mean? This means that in this, Z transform, I only have powers of, multiples of Z to the M, right? I have Z to the M, Z to the 2M, Z to the 3M. And the numbers on those powers correspond to the values of the original impulse response. And so if I think about what that means, this is like the Z transform, which I'm going to kind of denote by this curly Z, of what I'm going to call this expanded signal, right? So if I have my original signal, this is my original H, and I put it through this expander where I put zeros in the middle, this is like expanding the signal, right? So this is exactly kind of what happens to the Z transform, right? That's like saying that, if I expand by 3, then this is like saying I take H0 times Z to the 0, what used to be H1 times Z to the 3, what used to be H2 times Z to the 6, and so on, right? So it's kind of like the Z transform of a signal that's got the zeros inserted in the middle. Okay. And so let's actually figure out, what are the corresponding Z transforms of all these intermediate signals to ensure that we know that these things are equal, right? Well, so I'm going to kind of just keep this on here a little bit. So the proof, there's an extra O there. So, all right, so let's do the bottom one first, right? So what is my, frequency domain? So this is actually a good experiment, right? So remember on the first exam, I had this kind of thing where we were kind of switching back and forth between Z's and Omegas and stuff like that. So same kind of thing here, right? I'm kind of like assuming that we're kind of mature enough to be able to understand, how to take things in the transfer function domain or the Fourier transform domain. So here what happens is that this is like saying I have the original signal, and what is the corresponding thing when I have H of Z to the M? That's like saying I have the original frequency response multiplied by M, right? Because Z is E to the J omega, right? So this is what happens at this point. Now when I downsample by M, what I get are these copies, right? These periodic copies. And so I know that my result after downsampling is going to look like a whole bunch of periodic copies that are spread out and M, times shrunk. So I'm going to get these M copies of whatever this thing was that are going to be spread out and shrunk. Right? So these are basically spread out, shrunk copies. Okay. And I feel like I lost my H. Oh yeah, so and this is going to be multiplied by the same thing. If I plug in omega M here, what I get is this. Right? It's like I'm plugging in, the spreading out and the shrinking into here too. And so here, this thing, right, since I is an integer, I can kind of make this easier by taking this out of the sum. This is equal to H of omega times this guy. I guess actually I was a little bit quick here. So this is just the original x, not the xp. Hold on a second. Right, let me start this again because I feel like I'm this stuff here. Okay, let's try again. Proof. This time I'm going to put 4 rows in there for extra proofiness. Okay, so I was happy with this. I had my original signal and I had my h of omega m. Okay. Now, my y of omega is what I get when I filter, when I downsample xb. So what I get is I'm going to get copies of xb spread out. Okay, I think this is where I skipped a step on the previous slide. Now I'm going to plug in what I know about xb. I'm going to say this is like, I've got the spread out version of this guy and the spread out version of this guy, which because it was already, expanded, this is going to, have the result of the m and the 1 over m is going to cancel out. Now I'm going to say that since here, this is going to be the same as h of omega, since this thing is 2 pi periodic by definition, I can take out the h of omega. And then I can say, oh, this is actually h of omega times, well, this is exactly what I would have gotten if I had downsampled first, right? This is like the result of, let me show you again, right? So this is the result of if I had downsampled first, then I would have just gotten spread out copies of x, right? So this checks out, right? This is like saying that, if I compute what the output of this guy is, it's the same thing I would have gotten had I done things the other way around. Okay. So that's property 1. The other one is flipped around using upsamplers, right? So another one is that also, if I have this system where I put it through a filter, I get some signal, then I put it through this upsampler, and I get some numbers. That's the same as if I were to interchange, put the upsampler first, get some intermediate signal, and then put this through a Z transform like this. So let's prove why that's true. Okay. Well, again, I'm going to start with, let me start with the top guy, right? So that's like saying that my YA of omega, what do I get when I insert the zeros in the middle? Really all I'm doing is I am expanding, or I'm shrinking the frequency domain like this, right? So this shrinks the frequency domain, and then my XA is simply what I would get if I were to filter the original x with h. That's like saying I have x of omega L times h of omega L. Okay. Now let's figure out what the bottom one is. So my xb of omega is simply what I would get if I were to expand, or shrink down my original x, and then I'm going to filter it with this, which is the same thing as applying this frequency domain, and so these things are equal, right? So that was actually a lot easier to prove. And so what this means is that I can interchange the zero insertion process and the filter with just a little bit of a change of what filter I do, right? And so, as I'm going to show more in just a second, why would I want to do this, right? So one way I think about this is that this lower branch is kind of inefficient, right? In the sense that I am inserting a whole ton of zeros into my signal, and then I'm running that through a filter, right? And so the filter is dumb, right? The filter doesn't know any better when it sees an input. It just kind of grinds through whatever it knows how to do on the input, right? And so here, this filter would be applying a bunch of unnecessary computations to a bunch of zeros, right? And so computationally, that would be a waste of time, right? Because I should know that there really aren't that many non-zero entries in whatever the signal is, and so I shouldn't waste my time filtering, right? Instead, what I should do is, find a way to filter first and then insert the zeros later. Turns out that I get, these things turn out to be equivalent. And so both of these ideas that I just showed you are the root, or the way that we do what's called a polyphase decomposition of a signal. Okay. So we're going to put these identities in our back pocket, and now we're going to look and think about, okay, so suppose I have a system that I want to have a whole series of upsamplers, downsamplers, filters. How can I do that in an efficient way? Okay. And so the key idea is what's called a polyphase decomposition. Okay. And so the idea is, let's think about some arbitrary signal. Could be whatever, but I'm drawing it nicely to make it easier for me. So what I can do is I can think of this signal as the sum of a bunch of simpler signals, right? So I can say, okay, I can decompose this as the sum of m kind of subsequences hk of n, which are defined as follows. So I'll write down the math first, and then I'll actually show a picture that's easier. Right? So all this means is, let's suppose that my m equals 3. Okay? So what this is saying is, I am going to write this guy simply as the sum of 3 sequences, where the 0 one is just taking every third element starting at 0. I guess this was bad luck because there are some zeros here. The second one is taking every third element starting at 1. And the second one is taking every third element starting at 2. And so on. Right? So I can see that basically in this signal, these guys are the only potential non-zeros, and in this signal, these guys are the only non-zeros, and this signal, these guys are the only non-zeros. And so it's pretty clear that when I add these 3 guys up, I get back my original signal, right? So all I'm doing is I'm kind of taking apart the original signal into the sum of these guys here, okay? And so what I can say is I can write my original signal as the sum of m subsequences. And actually, let me just be a little bit careful here. All right, actually, I screwed this up. So this is true. What I want to kind of say is that this is like this. What I want to do is I want to talk about the sequences as if they all start at 0. So my actual H0, H1, H2 are these things centered, so they always start at 0. So my H0 then is the same. My H1 is basically something where I take every third element. So what I'm doing here is I'm just kind of making sure that always it's the multiples of m that have the non-zero parts. Oh, I must have gotten some crap on my hand there. And the same kind of thing with this. Right, so the idea is that if I want to reconstruct my original signal, what I need is to take h0 of n, and I need to take h1 of n delayed by 1 unit, and I need to take h2 of n delayed by 2 units, right? So a different way of writing that is just the sum from k equals 0 to n minus 1 of hk n minus k. Okay. And the idea here is that I can go from these signals that have too much space inside of them to 3 subsequences where I remove all the zeros from the middle, right? So I can relate these h's to what I'm going to call e's. So my e's are basically just going to be what I get by downsampling my h and taking that every m units, right? So for example, my E0 of n is simply going to be these entries of h, and I'm going to say, you know, I'm going to take them every third unit so that I never get any empty space, whatever this turns out to be. This is basically like removing the zeros from the HKs. Okay. So now I am going to write a complicated block diagram that is just kind of like refreshing our memory of how all this stuff works together. Okay? So it's like saying what I could do is I could take my original signal. Actually, let me put my original signal at the top of the page. So to get my first polyphase decomposition, what I would do would be say, okay, I am going to downsample that by a factor of m, right? That's going to give me what I called E0 of n, right? That's like saying, take my original signal, right? Take every third element. That's exactly what I would get with this E0, right? So this to this is just simply straight out downsampling every mth element. Okay? And then if I wanted to reconstruct my original signal, what I would do is I would insert zeros between those guys. That would give me my thing that has the spare zeros in it. And now I'm going to wait and I'm going to add that up with other parts of the decomposition. So the next thing I would do is I would say, okay, I can delay, or I can kind of shift the signal by 1 unit. I can downsample that. Then I get, so what I get by shifting this is something basically that's just like shifting the signal 1 unit to the left, right? And then I pick off every third unit or every mth unit there. That gives me this E1 part. And then if I wanted to put it back together, I would upsample. I would take this thing. I would shift it. I would delay it by 1 unit. And then I would add it up to this. And so I can kind of draw by a diagram that says, okay, this is what I would get if I were to do the 2 decomposition and so on. And this keeps on going for however many of these polyphase pieces I have. And after I add all that junk up, what I get is exactly my original signal, right? So this is just like an extremely fancy and seemingly time-consuming way of taking the signal apart into the smaller pieces and then putting it back together, right? So in some sense here, right, these guys down the middle contain exactly the same information as the original samples here, right? It's just basically taking those little M strings and writing them, so in theory, if I had, 30 elements here, and I would downsample by a factor of 3 in these blocks, these guys, I would have 3 length 10 subsequences, right? And this part over here tells me how do I put those subsequences back together to obtain my original signal, right? I expand them by putting the zeros in, I shift them so that they're in the right place, and then I add them up, okay? Okay. And, if I wanted to, just as a quick note on this, I could make this structure even more efficient, basically by, instead of kind of explicitly delaying h by nothing here, and then by z here, and then by z squared here, I could, for example, kind of rewrite this as saying, okay, I kind of have a set of chained delays. So let me write this in a slightly more efficient way. That's like saying, okay, my first branch, I don't do anything, and that corresponds to the same thing here. I downsample, then I upsample, then I get my guy here. Then here, what I would do is I would delay, or I would delay the signal, but it's like shifting it to the left instead of to the right. What I get here is h of n plus 1. I downsample, I upsample, I get this. And then I would need to delay this guy. Here, since this guy has already been delayed once, I can just insert one more step here. And so on. Actually, the way I should do this, I guess, is I should put the delays like this, right? So that here, this guy gets delayed, and it gets delayed again when it passes through here. And this kind of goes on until I finish my structure. So all these guys kind of get added up as I go. And so this is basically the same system with what I'd call chained delays, where instead of having to explicitly delay this guy by some large number of z, instead I kind of am incrementally stepping through every time and doing a delay by 1, delay by 1, delay by 1. And in the same way here, instead of having to shift this guy by some different amount every time, I just always shift it by 1, and I keep on shifting as I go back to add up. Okay, so far this seems like pretty useless, right? Like, why did I even bother to do this in the first place? Okay, so let's kind of think about why this is going to be working for us, right? So let's refresh our memory that what I really care about is what I would call these guys in the middle, which are the polyphase components of H. So those guys are defined as taking every mth element of H, but shifted by K, which is the same thing as taking my guys with the holes in them and taking every mth unit. So these are called the polyphase components. of h of n. Okay. And what I care about is, what I'm going to try and do is I'm going to take a system and I'm going to decompose it into its polyphase components, right? So for example, if I want to be really precise about this, I can say, okay, if I have, what is my Z transform of this filter, for example? Well, it's defined as this guy. And I can write this as the sum of a bunch of M Z transforms, right? What I could do is I could say, okay, I'm going to take the sum over just the guys that are multiples of M, Z to the minus LM, like this. And then I'm going to take just the guys that are multiples of M plus 1 times the corresponding values of Z, and so on. And then I could say, okay, well, that's like saying that I can write this. I have exactly capital M of these guys inside the sum. And each of these guys looks like a Z transform like this, where I have LM plus K, Z to the minus LM plus K. And I gave each of these guys a name, right? So this guy here is exactly the polyphase component here. So this is like saying, I'm going to take out this Z to the minus K. I'm going to have something like this. Z to the minus K. Then I have this guy here. And that's exactly the definition of the Z transform of this guy, just with multiples of powers of Z. So what I have here is this sum, Z to the minus K, and this is exactly the Z transform of the polyphase components shifted or taken to the power of M, right? So this is kind of the way I set things up. This is like saying that if I wanted to filter the signal with this filter H, so to sum it up, it's like saying in the frequency domain, or in the transfer function world, that's like saying that H of Z is related to the Z transforms of all of the subcomponent little pieces by this. And that means, for example, that I could take an input signal, and what I would do if I wanted to filter things here would be I would multiply this guy by E0 Z to the M. Then I could delay this by 1 unit and multiply that by this guy. Then I could delay this by 1 unit and multiply it by this guy, and so on. And then I would add all these things up to get my filtered signal, right? So this is kind of an equivalent way of writing the Z transform. I take the Z transform apart into M easier Z transforms, right? So this is called the polyphase realization of H of Z. And so one of the homework problems is to take a simple filter and show me how to take it apart into these, for example, 3 polyphase pieces. And then you can kind of see for yourself how the pieces come apart. Okay, so now let's kind of put it together and think about why did we want to do all this stuff in the first place. Okay, so let's consider a system in which I have to filter and then downsample. Okay, so now we're going to talk about the polyphase implementation of these kinds of decimation or interpolation filters, right? Upsampling and downsampling filters. Right. So suppose that we want this. Suppose we have a system where I take a signal, I put it through some filter. So let's call this, Y. Then I downsample that, and I get some, downsampled guy here, right? And so here, originally, if I was taking samples, every 1 unit, and here I'd be taking samples still every 1 unit. After I downsample by m, that's like saying that the rate of this signal is 1 over m, right? So this implementation, as written, is kind of a dumb thing to do, right? That's like saying I take my long rate, my signal that's dense with samples, I filter that so I get lots of more samples, and then I throw, basically all those samples away. I'm only keeping every mth sample. So why did I bother to generate all that stuff in the beginning if I was just going to throw most of it away, right? That is an inefficient representation of this kind of process, right? I shouldn't have to generate stuff that I never use, right? And so that's where the polyphase, thing comes in. So here, in this form, we're throwing away, we're generating, and discarding a fraction of m minus 1 over m values, right? So how would we make this process easier? Okay, so what I'm going to do is I am going to write this filter in polyphase form, okay? So now instead what I'm going to do is I'm going to have my incoming signal. Polyphase tells me that I'm going to put that, so again, let me just put this back on the board. So I'm going to put it through this guy here, right? I'm going to put it through this. Actually, I think these should be pluses instead of minuses. So I'm going to put this through a cascade of shorter filters. So I'm going to put this through this guy here. Then I'm going to put this through this guy here. And so on. And then, what I would do is I would add up, I would downsample these guys and add up the result to get my output. And so here, this is like saying, okay, well, if my original rate here was 1, I'm going to be taking each of these guys, and each of these is going to be just like, again, filtering this rate 1 signal, so the rate here is still going to be 1. Then after I downsample everything, the rate is going to be 1 over m. Now what I'm going to do is I'm going to say, well, I've got exactly the setup that I had in the identity that I proved earlier, right? So I had an identity that looked like this, right? This is exactly the setup where I had something that said this system was equivalent to this system. And so I'm going to apply that right here. It's like saying, okay, instead of doing this, I'm going to flip these guys around. So now we find a more efficient equivalent system. What I would do is I would interchange these guys and say, okay, instead what I'm going to do is I am going to first up here downsample my signal, right? Then I'm going to filter it with this shorter Z transform. And the same thing applies here. So I'm going to downsample, and I'm going to filter this with this guy. And again, I'm going to add these guys all up at the end, and that's going to give me my output. And so this is a lot more efficient, right? This is like saying, I take my original signal, and now I am going to basically take my original signal, I'm going to make it into M shorter subsequences, right? So now each of these guys is going to be at rate 1 over M. I'm going to filter each of these guys with a shorter Z transform that doesn't have any fluff in it. There are no, this has powers of Z every integer unit of Z. And then my output is going to be at the right rate, right? So the idea here is that in this form, I'm not generating anything that I'm not using, right? I'm not throwing anything, I'm not throwing any of my computed values away. The only thing I'm throwing away, I guess I'm not really throwing anything away, right? All I'm doing is I'm taking the input and I'm shifting it around, and then I'm filtering each of those little guys with a shorter filter, right? So the idea is that suppose that, if my original H of n was, say, an n point or an n tap FIR filter, each of these EI of n's is an n over m tap filter. And so my original realization would involve basically my original realization would involve n multiplications per unit of time, and my polyphase realization would involve n over m multiplications per unit time. Right? So I'm saving a factor of, m multiplications per unit time, which is a real advantage, right? So in this case, the advantage comes from the fact that I'm never filtering anything that I don't need. And the same way, let's suppose that I had a system like this where I wanted to upsample and then filter to get my output, right? And so again, here's a situation where, as written, this is a wasteful thing, right? Because this is like saying that when I upsample, I insert, so here, L minus 1 over L of these values are going to be equal to 0, right? And so the filter, if this is just some sort of hard-coded filter, it doesn't know that, right? It's just going to be grinding through, multiplying lots of things by 0, wasting a lot of time, right? So why would I multiply these zeros explicitly if I could rearrange my computation to avoid that kind of needless stuff, right? So when I filter, I'm wasting a lot of time here. So we would be filtering mostly zeros. So instead, I would use, again, the polyphase realization of this filter to be smarter, right? So again, if I expand this into my polyphase representation, that would be like saying, okay, I'm going to split my x of n into a bunch of pieces where I'm going to think about it as, a bunch of upsamplers like this, each of which gets filtered by a piece of the polyphase guy. And then to put things back together, I have to delay these guys and add them up. Dot, 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 dot. And so what I would do is I would say, okay, well, why would I not just flip these guys around? So again, using the other identity, we're going to flip the upsampler and the filters. So using that, I would say, okay, I'm going to take my signal, I'm going to filter it by a bunch of shorter filters. And then I'm going to upsample each of these to put the zeros in. And then I'm going to delay these guys to put them back together. Dot, dot, dot. So again, here, all I'm doing is taking the original signal, filtering it by a bunch of shorter filters, and then I am just shifting and adding up these guys here, right? So the idea is that here, no zeros are explicitly filtered. And again, that realizes a computational savings, right? Because here, if this was at rate 1, then this was at rate 1. When I upsample, now I have rate L. And so here, I'm not doing any operations really at the higher rate. I'm only doing all my operations at the lower rate. Okay. And so this is the fundamental, that's really all I want to say about how this kind of polyphase process works. But the idea is that, now if I have a more complicated system where I'm, where I have the foreknowledge that I'm going to have to change my sampling rate and do some filtering and change it back, right? I can be shrewd about the way in which I can order those systems so as not to waste any computation. That's the kind of upshot of things, okay? And so what you're going to do on the homework is just one simple example of just showing me how to take, a long filter and make it into these 3 shorter filters and show me how it works in the frequency domain, or in the Z domain, I guess. Okay. So again, I know this is the kind of material that's kind of tough to assimilate the first time you see it, but that's why we have, other materials like the textbook and like, well, I don't want to say Wikipedia because we just showed that Wikipedia was wrong about some stuff. But, you need to kind of look and see, okay, convince yourself how these filter diagrams work. So one thing that I'm not going to emphasize a lot in this class, partially because I find this kind of material a little bit tedious, is different realizations of filters, right? And that's a good project idea also, is to think about what is the most efficient way to arrange DSP computations, right? Because if you're putting, if you're actually implementing this with parts on a board or, or a Simulink block structure, you want to do that set of computations in the most efficient way that you can, right? And so this polyphase decomposition is one example of a way to squeeze unnecessary computations out of the process. And in a way, the FFT that we talked about, earlier is another kind of way of saying if you were to naively apply the DFT formula, you'd be wasting a lot of effort because you'd be doing a lot of unnecessary multiplications, right? So kind of the theme of both polyphase and FFT is filter structures that make computational sense, okay? And again, if anyone wants to kind of explore this idea further in a project, then that would be great, because there's a lot of stuff that's in these chapters of the book that I didn't touch on at all. There are lots of interesting connections. So like if you guys have ever heard of like filter banks or quadrature mirror filters or wavelets, all those kinds of things are related to this concept of taking a signal and breaking it up into decomposable parts and doing efficient computations on those parts, right? So you can kind of flip through, I don't know if it's chapter 10 or chapter 11 in Proegus, that gives you some intuition for other ways in which these kinds of things might be used. So even though this looks kind of messy, if you kind of flip around the book, you'll see lots of structures like this throughout. And that's kind of what some more advanced DSP stuff is all about. Okay. So questions about polyphase, multirate stuff? Yeah?
Just clarify real quick. That continues on until E sub L minus 1.
Yes, right. So these dot, dot, dots go all the way down to E sub L minus 1 of Z, right? Because I have basically L shorter filters, right? Yeah. Yeah, this is the kind of thing that kind of lends itself more to ready-made PowerPoints than doing it by hand, but I like to do stuff by hand. Okay, so let me stop this guy, and